Welcome back, everybody. And for those of you that are new, welcome to our science phenomena from the field. My name is AJ Long. I work at DRI, and we have a few housekeeping things. I know you guys, some of you have heard this before, but we do have some new folks. So I just want to make sure we're all on the same page. If you can leave your video on, that's great for us because it feels more interactive and it helps with our scientists seeing your faces. We record the sessions so that we can present them later. There are teachers that wanted to be here that couldn't make it, so we're going to make them available. Making sure your Zoom name matches the name you signed up with would be great. When you have questions, feel free to put your question in the chat box. At the end of Dr. Bacon's presentation, Megan will call on you. Call on those of you that have questions that she knows he can answer, and she'll have you unmute yourself and start your video so we can see you, so that'd be great. We have closed captions available, so that's at the bottom of your screen. You just have to click closed caption and how you want to see it. Thanks to Chelsea for typing for us. And again, we have a raffle. We are raffling off another 5 gift cards to Amazon for 20 bucks each. Must be present to win. So that's exciting. At the end of a link to the Google form for a quick evaluation. It's like 6 questions. It'll take you no more than 2 minutes to finish. We really appreciate the feedback. It's been overwhelmingly positive with some great suggestions about what your needs are, because as you know, as a science institution, we really want to support you. So any insight you have to what other resources we can provide for you or trainings, let us know. And just to remind you, for today is for you to meet a real live scientist who works at DRI with very Nevada focused research so that you can learn a little bit about what's happening in your state. To hear about phenomena, I know teachers have questions about how do I integrate this into my classroom, and those are great questions. We won't necessarily answer those. This is really about you learning from a scientist what's happening, and maybe get your brain turning on how you can turn your kids on to real life science and you can integrate it into your class. But it's a great idea for another time. So without further ado, I'm going to introduce Steve Bacon, Dr. Steve Bacon. So he's going to tell us a little bit about what he does at DRI and where his story began with science. Take it away, Steve.
All right. Well, hello, everybody. It's nice to see a lot of faces here. Seems like it's been a long time since I've seen this many faces in one place. So yeah, so I've been at the Desert Research Institute it will be 15 years this July 1st. And I am a research geologist there. My specialties, or my discipline, is in quaternary geology and paleohydrology, and that's kind of the pure research that I do. The applied research I do is related to geologic hazards, and that in particular seismic hazards. And let's see, where did it all begin? Well, you know, I went 4-wheel drive camping all the time with my dad, and it was out in the desert. And all us folks that live in Nevada, especially down south, Las Vegas area, there's no vegetation, so you can see the geology. It's everywhere. And my dad was an amateur kind of rock hound, so as we're driving across the desert, he was constantly pointing out things. Oh, look at that mountain range. Oh, you see all that sediment coming out of the valley. Well, that's an alluvial fan. And oh, you see how flat that area is? Yeah, that's an old playa basin, you know, an old dry lake bed. And that happened for as long as I can remember. That's all I heard was just kind of the driving across the desert. So then that, you know, that was a major influence with my dad. And then in 10th grade, the high school I went to, they offered a variety of different science-based classes. I think there was a physical science, there was biological science, or actually no, it was marine science, and then there was earth science. So I elected to take earth science. And my teacher, Mr. Kingsley is his name, he was a retired mining geologist, a petroleum geologist. And I look back now, and he was actually pretty young. As a 10th grader, he seemed pretty old, but he was young. He retired early, and I guess he decided he wanted to be a teacher. He wanted to teach geology to high school kids. And his approach was really laid back and interesting. He intrigued all of us, and this was many moons ago. I'm trying to remember, but he made an impression on me that I still remember. I just remember him just sitting back and lecture with his feet up on the desk and showing slides. This was back in the day when there were slides. There wasn't a television that he could show PowerPoint. And he just taught geology by showing examples. We had a textbook, and it had all the information that geology books have. But it was really educational. I'll just say that he showed an example, like with a photograph, something that we could all relate to, especially if, we've been outside, like all of us. That's one thing that I've always mentioned about geology is we all are geologists at some level. If you go outside and you observe, you can see and touch. We've all picked up rocks and thrown them. Geology is just telling you what that type of rock is, terminology, stuff like that. So, it's really easy to relate to. And Mr. Kingsley, he did a good job. And I'll never forget this. So in our yearbook, so this would have been after 10th grade, our yearbook. Everyone signs your yearbook, right? And if you have a favorite teacher, you ask if they'll sign your yearbook. Well, Mr. Kingsley was my favorite teacher in 10th grade. So I asked him if he would sign it. And listen to this was pretty cool. He wrote, "Steve, one day you'll make a fine geologist." And I have that. And it wasn't until after I got my undergraduate degree at Humboldt State University, which is in Northern California, I remember thinking, oh, somebody wrote in my yearbook. And I went and when I went to visit my mom, like a summer break, went through the yearbook, and sure enough, that was like for real. So that was really cool. So, there was my dad, and then there's Mr. Kingsley, my 10th grade teacher, earth science teacher. And then it wasn't until undergraduate where my mentor, Dr. Bud Burke, he was the one that really launched me into, wanting to do geology. And it was kind of funny because I remember I didn't even want to go to college. Like my mom was like, she's like, "You're going to college, I've worked hard and all this, and you have to go to college." And at that time, I was thinking about joining the Marine Corps. I mean, I had an uncle who was in the Marines, and all that. But he said, my mom was like, "No, you're going to college. If you want to go in the Marines, be an officer, finish school." And I remember on my college application, I probably shouldn't say this, but it asked, what do you want your major to be? And really, I wasn't thinking that I wanted to do geology at that time. So I just knew that I wanted to do something in the environment. I wanted to get paid to go hike, essentially. So I wrote down environmental science. And I misspelled environmental. I forgot the N, right? And I still got in. But yeah, it was Humboldt State that really, made me figure out that I want to do geology. It was something that, interested me. And being in Northern California, it's pretty remote on the coast. So if you don't know where Humboldt State is, it's in Humboldt County. It's like a 6-hour drive north of San Francisco on the coast. You know, it's about an hour and a half south of the Oregon border. So it's remote. So all the geology classes that they offered there had a heavy field component to it, which would have been analogous to Mr. Kingsley in 10th grade, showing slides, photographs, right? But in college, we were able to get out and actually, dig in the dirt, smash some rocks with hammers, and learn that way, hands-on. And it was Bud Burke, my professor there. And I ended up going back to Humboldt State for a master's degree. I didn't have, I wasn't finished. I needed seconds. And sure enough, worked with Bud, and he took me to New Zealand. We went to Mongolia on research projects. So he exposed me to a lot of interesting things, a lot of research.
And didn't you just finish your PhD?
Sorry?
Didn't you just finish your PhD?
Yeah, right. So make a long story even longer. So then I did consulting after my master's. So that's geologic hazards. And I always wanted to get a PhD, but it just, I was working and doing stuff, and I moved to Reno, and I was still doing consulting. And then I got on a board with DRI. And so after working close to 8 years at DRI, I decided to go back to school. And then, just this semester, got the PhD that I put off for years. So
congratulations.
So you can do it, even as a mature student, I like to say.
Well, and that's great. And I feel like, as a lot of us are parents and we're teachers, some of us have PhDs and master's degrees. So I think it's really important to hear about that role modeling piece, because it is so important to kids to be supported. That brings us to the next question, which is, today we're here to talk about phenomena. Can you tell us about your one phenomena that you study in your work as a scientist?
Right. So phenomena would be, generally speaking, mountain building, right? We all can relate to mountains, especially out west. They're everywhere. They're considered beautiful, majestic. They're also fun to play in, right? You can ski, hike, camp. But also they pose geologic hazards, so they're relevant to society. Right? There's earthquake hazards, landslide hazards. In the wintertime, there's avalanches. There's also floods when it decides to rain around here. Right? So understanding mountains is important to society.
And I think too, a lot of kids do engage with our landscape. Nevada is the most mountainous range in the lower 48. So it does help us all connect. In terms of, why do you think this is a good phenomena, a good example of the skills needed to figure it out? Like, what is the relevance and the connection to kids and to people about how mountains are formed?
Well, students can look at mountains as natural features in the world around them, and then they can ask those questions that, what are the forces that drive or drove the formation of mountains? And then after asking that, then they can ask, what is the information or data that's required to actually answer that question of the formation of mountains, or how they are built. If that makes sense.
So let's dig a little deeper. What is the pattern that you study related to this phenomena?
Well, in particular, and it started with my master's research, and that's the study of paleoseismology. And paleoseismology is the study of ancient earthquakes. essentially what you do is you reconstruct the earthquake history on a particular fault. And how we do that is by, and if you have a large budget in a project, you can get an excavator or a backhoe and you dig a trench across the fault zone. And then you map the offset or faulted layers, the deposits, and you identify what deposits are faulted, and then you do your best in dating that deposit, getting its age. And then you also identify deposits that are not faulted, and then you get an age from that. And from that two information, you can constrain the timing of an earthquake. And then from that information, you can then provide the information for seismic hazard assessments. So effectively what you're doing is you're determining how active a fault is. You can do like a really highly active fault, like the San Andreas fault. That's extremely active. It's had historical surface rupture, in the 1800s, in 1906 even. And then you dig across the fault and you determine that on average, you have a recurrence interval like between 300 and 600 years. And that's a major plate boundary, so it's highly active. But out in Nevada, out in the Basin and Range, recurrence interval on faults is much longer. And you can have earthquakes occur on faults like every 3,000 to 6,000 years, relatively speaking.
Do you want to show us the slide that you have? That might be a good.
Yeah, well, I can show that in a little bit.
Okay.
If that's okay.
Sure. So the next question is, an investigable question is one that students can answer through systematic observations and interpretations of their data. What is it about this phenomena that provides investigable questions?
Yeah, right. So when I was thinking about what would be an interesting topic, naturally for me, it's earthquake hazards. But from in middle school, even elementary school, middle school through high school, you learn about earthquakes. And if I recall, it was always within the context of like shaking and destruction, right? You have large earthquakes, they shake and buildings come down. And if you're in school, you duck, cover, and hold on, right? So, and then you'll see maps of like the distribution of seismicity, right? The earthquake epicenters. And they all occur around the Ring of Fire, right? So when coming up with this phenomenon in mountain building, I wanted to kind of put it in the context of earthquakes, but not shaking, right? It would be more like you have a mountain range, and then you got to think, how did that mountain range form? Well, naturally you think, well, it popped up, or it's uplifted, or depending on where you are on the planet, you have two plates and they collide, right? But really, here in the Basin and Range in Eastern California and Nevada, it's from earthquakes. And it happens over long periods of time. So a question that could be posed is the relief of mountain ranges a function of the activity of faults adjacent to the mountain, right? And relief is the difference in height relative to surrounding terrain. So the hypothesis would be the higher the relief of a mountain range, the higher the activity of the fault is, if that makes sense.
It does. So when I think about Mount Whitney, right, is the highest point. So you're saying, is that the most active place for plate movement? Is that correct?
Yeah, right. Yeah. So Mount Whitney in the southern Sierra Nevadas, that it has the Sierra Nevada rangefront fault right on the east side, along with the Owens Valley fault. And the Owens Valley fault last ruptured in 1872 and produced the third largest historical earthquake in California, just for a relative sense. So, the fact that the highest point in the lower 48 has some active faults adjacent to it is no surprise. And one way you can test this hypothesis would be to make measurements, to collect data. And that would fall under producing systematic observations. And one way that we do it as geologists is you can take topographic maps or use ArcGIS, which is software package where you can measure elevations. Or what's really convenient is you can use Google Earth, which anybody can use, and you can use it in the classroom setting. It's a really powerful tool. In fact, to be honest with you, it's much easier to use than ArcGIS, at least on a kind of a general kind of approach. And what you could do is select a couple of areas within Nevada and Eastern California, and what we call it our transects, essentially a line over a certain distance. And you can select maybe 3 transects or lines that cover like Mount Whitney area in Eastern California, all the way through Nevada. You can go further north, like near Mono Lake area, and do the same thing. Essentially, you're starting your transect on the Sierra Nevadas and heading east across the Basin and Range. And then you can do another one up in the Reno, Carson City area. And students can actually measure the relief or the elevation difference between the ridge crests on the mountain range and the valley bottoms. And you can systematically measure across your transect. So you'll have elevation differences. And that would be like your systematic observation. That's collecting your data. And one way to test that, your hypothesis, the hypothesis that the higher your relief, the higher the fault activity, is that you can then plot the locations of USGS faults of the area. And those have all been classified by activity. They're classified under historical, meaning that they've had a surface rupture in the last 200 years. There's Holocene activity. Those are faults that have had at least one Holocene earthquake, and that's a period of the last 12,000 years. And then there's late Pleistocene activity, and that's between 12 and like 150,000 years. So they've classified these faults in their relative activity levels. And you can plot that up on your transects, and then you can start you could correlate the relative degree of activity with the relative relief that was measured, or where the students measured. And then, yeah, you can start testing that hypothesis, see if it holds up. And maybe this would be a good time to show some examples.
Great.
All right, so I'm going to attempt to share my screen here. Let's see if this works out. All right, stand by here. Oh, it helps if I hit the share button here. All right, can everybody see this?
Almost. It says, yep, here we go. There it is.
Okay, all right. So this is a screenshot of Google Earth Pro. And I'm sure many of you are aware of Google Earth. If some of you aren't, this is an app that you can download for free. And it is a powerful way of viewing the globe. It's great. You can get lost just cruising around looking at stuff. So this is an example of imagery from California and Nevada, and what you can see are different colored lines, and those are all the faults within the USGS fault database, and the color coding is the relative degree of activity. For example, the red are historical ruptures or historical earthquakes. And can you see this cursor moving? Yeah, okay. So we're talking about Mount Whitney, and Mount Whitney is right here. So for to place yourself, here's Lake Tahoe, here's Reno, and then Las Vegas is over here. Just to place yourself. And Mount Whitney is right here, and this is Owens Valley. I'm going to move to the next slide because it's a closer view of that area. At least I'm trying to here. Here, stand by. All right. Okay, so there's a closer view. So here's Mount Whitney right here. Shows these big mountain symbols. Here's Mono Lake for perspective. This is the Owens Valley here. And in red, this is the map trace of the Owens Valley earthquake in 1872 that I mentioned earlier, right here. You can see there's also been some historical surface rupture here. This is the Long Valley caldera. Mammoth Mountain right here, the ski resorts right here. This earthquake, there was a series of them in 1980. And then there's some more earthquakes that occurred, well, one in particular in 1986. And then some of you, probably in the Las Vegas area, remember the last July, it's almost a year ago, there was a magnitude 7.1 Ridgecrest earthquake. That's just to the south in Indian Wells Valley. So here's a really great data set that can be used in the classroom setting where you have imagery, and you can get these fault locations from the USGS. And with respect to a transect, so a transect is a line. And you can see the yellow line. That's essentially a west to east transect across the Sierra Nevadas. And this is a view in Google Earth looking to the north, but with an oblique view, you know, as if like you were in a high altitude plane, you know, flying high. And below is the profile. It's a geomorphic profile along that transect. And in the imagery, you can see there's a red arrow. And that red arrow I placed there to show you the location of Mount Whitney, just for perspective. And you can see that that red arrow has a gray vertical line on the cross section, shows you your placement. And you can actually move that arrow left and to the right, and it will tell you your elevation. It's really neat tool. So that's a way that you can identify the highest point on your profile and your lowest, and you can calculate your relief, you know, your difference in elevation. So this is an image that doesn't show any of the faults. And the next one, the next image does show the faults. And in particular, I moved the red arrow to the location of the Sierra Nevada frontal fault, which is shown in orange, and that represents historical fault activity. It's had at least one earthquake or surface rupture event in the last 12,000 years. And that red arrow on the profile plots right at the foot of the escarpment there. So you can see there's high relief right adjacent to the location of that fault. And then further to the east, actually I have a bunch of faces covering it, but you'll see that there's another fault, not the red one, that's the Owens Valley fault, but over in Saline Valley, you'll see there's another escarpment that looks similar to the Sierra Nevada escarpment. And there's also a fault associated with that. Here's an example of another transect to the north and within Tahoe Basin. And similar to the Sierra Nevada range front in the south, in Owens Valley, you can see that there's a big escarpment, and then sure enough, where the arrow is pointing, that's the Carson Valley fault zone. Sure enough, there's a fault there with Holocene activity. And yeah, so those are some examples of the use of Google Earth and the USGS fault database to be used to, you know, verify or validate a potential hypothesis that's been presented. So.
Awesome, thank you. We have two more questions. So if teachers, if you have questions, you can start putting them into the chat. Steve, my next question is, in the course of your career, I'm sure you've generated many research questions. What do you think makes a good question? And what are some common errors?
All right. You'd probably spend a career trying to figure that one out. I think the number one, a great research question would be one that actually interests you. You know, if you have passion for something, it could be anything, but you have passion about wanting to answer, or, you know, you're just curious, that typically drives a really good research question. And what was the second one? What's not a good one, or what?
What are some common errors?
Oh, common errors. I think a number one common error would be what we call model chasing. That is having a preconceived notion of the answer without supporting data. And you might feel very strongly about something based on your experience, but it hasn't been shown or demonstrated with data. But one thing that makes science not so straightforward is that there's a lot of interpretation, especially in geology. You know, you're trying to interpret what happened, let's say 15,000 years ago, right? You might collect a robust data set of physical information that no one would dispute is incorrect, but it's how you interpret it, right? Somebody might interpret data. Let's say you go up to a stream, so you're in a stream channel and there's a cut bank, and it's like a 10-foot cut bank, and you see a bunch of deposits, a bunch of layers of sands and gravels. And you know, at one point in time, there have been lakes, like old ancient lakes, but now there's a stream. Well, sometimes lakes and streams can deposit the same type of deposits, right? It could be sands. So it's up to the geologist or scientist to interpret that those are sands deposited by a stream, but someone else could say, well, those are sands deposited along a shoreline of a lake. Yeah, right. So now you got to find even more information to dispute one or the other. And sometimes that's difficult because, at least with geology and another reason why I enjoy geology, it's like a scavenger hunt, to be honest with you. You know, you're running around, poking around, digging around, looking for evidence. So, yeah.
I'm curious, teachers, there's a reaction button on the bottom and there's options, but like thumbs up if you guys teach geology or faults in your classroom. I'm just curious. You can do this just to get a visual. Some do, some don't. Okay. There are lots of thumbs up. Okay. Looks about 50%-ish, maybe a little more. Okay, great. So Steve, the last question is, in terms of your job, a big part of it is mentoring future scientists and teaching people how to think. What mentorship advice do you have to help students move from memorizing to actually asking questions to figure something out?
Yeah, that's a really good question. Me personally, I've never been good at memorizing. It's just how I'm wired. I work. What works best for me is understanding the fundamentals, kind of the principles, the guiding kind of ideas, and then once I have an understanding of that, then I can start doing a better job memorizing. But with respect to mentoring, I haven't had students to mentor, but in the workplace, consulting, and also at DRI, I've been crew chief, and I've managed others. And the best way to mentor is lead by example, and be passionate, and positive, and allow people to figure it out on their own a little bit with some guidance. If you see them stumbling, I mean, you don't want them getting bruised because they're stumbling so much, but you have to allow a little bit of time for them to figure it out on their own. Otherwise, they won't use their own kind of knowledge in figuring it out.
Great.
So yeah, micromanaging has never worked well for me, so I'm not a very good micromanager myself.
All right, thank you, Dr. Bacon, for your insight. Megan, I'll turn it over to you. And teachers, this is a good time to type in if you have questions specific to anything Steve's talked about today. And she will call on you. Just make sure you unmute and start your video.
Awesome. Thank you, AJ, and thank you, Steve. This is great. So the first question comes from somebody who doesn't want to ask it themselves, but so I'm going to ask it for her. She's asking, where have there been recent earthquakes and what impact have those had on the nearby ranges? Does it trigger other movement?
What impacts has it had in?
Yeah, so she's asking where are the recent earthquakes taking place and what impact have they had on local ranges or the ranges nearby?
Oh, right. Yeah. Okay. Yeah, sure. All right. So almost going on a year ago, there, like I mentioned earlier, there was the Ridgecrest earthquake, and that was there was actually two earthquakes. There was a 6.4 that occurred on July 3rd, and then there was a magnitude 7.1 that happened in less than 24 hours later on July 4th. And I'm sure many of you folks in Las Vegas area may have felt it. That occurred within Indian Wells Valley, which is in a valley adjacent to the Sierra Nevadas. And that had a maximum vertical displacement of nearly, I want to say, like 10 to 15 feet. So the range on the upside of the fault went up relative to the downside. So it actively helped form Indian Wells Valley, essentially make the valley a little deeper. And then more recently, there actually was the earthquake just east of Mono Lake. I think that was about a month ago or so.
The one near Tonopah?
Sorry?
The one that was publicized as near Tonopah?
Yeah, that's right. Yeah.
Yeah.
I believe that was a 6.4. Yeah, and that was the largest earthquake to affect Nevada in 60 something years, I think, since 1954, however many years that is from now. So yeah, and that particular fault, that earthquake occurred east of a mapped fault. There was no mapped fault associated with that earthquake, and for the size, for a 6.4, it had relatively little surface rupture associated with it. So it's really perplexing. All the earthquake geologists are scratching their head, going, "What on earth happened here?" They sometimes characterize it as a blind fault, meaning the fault plane didn't really reach the surface like you'd expect for a magnitude 6.4. So in terms of seismic hazards, it's like, wow, not all faults are mapped. In fact, that magnitude 7.1 earthquake at Ridgecrest, only a couple pieces of that fault were actually identified. So that was a new one.
It's really interesting. That reminds me of the earthquakes in Christchurch a couple of years ago. I don't know, were those blind faults also?
Which I didn't hear.
Earthquakes out of Christchurch, New Zealand.
I think those might have been blind thrusts.
Awesome. So I've got some really interesting questions in here. Christy, do you want to hop on and ask your question about elevation changes?
Sure. I wanted to know if there are elevation changes occurring in the Nevada mountain ranges. If so, what are the trends? And are any of them related to prolonged drought?
Wow, that's a really good question. So the Nevada Bureau of Mines and Geology, along with the USGS, they set up GPS instruments all across the basin range, right? And these are permanent stations. They also do campaigns where they set up temporary stations that they leave up for about a week. So they have this large survey network, and a lot of these sites are on top of the mountain ranges, and then some are also on relatively stable areas in the valley bottom. And they measure the relative movement, the differential movement across all these mountain ranges. And many of these mountain ranges are going up and some are going down, but a lot of them are translating. They're moving horizontal, which is real interesting. Like, because we're close to the plate boundary where the San Andreas is, which is lateral fault, moves horizontal. Well, basin range is also moving horizontal. So yeah, they're moving up and down at really, really small, we're talking less than like millimeters per year. But over a long period of time, it adds up. And with respect to your question about drought, that's really interesting. In fact, Bill Hammond at the Nevada Bureau of Mines and Geology and UNR, he's a geodesist. He's one of the GPS kind of tectonic folks. And he came out with a paper not too long ago where he showed or demonstrated that under the drought conditions, the Sierra Nevada in the area near Mammoth Mountain was moving up at a faster rate than during wet periods. And he surmised, or his hypothesis was that there was less water content, less snowpack weighing down the crust. So under wet conditions, there's more water, and water weighs, has weight. And over a broad region, that weight adds up and it depresses the crust, the lithosphere. And when there's less water, there's less weight and it pops up, kind of isostatic rebound. So yeah, so there is a response.
That's amazing. Wendy, you have a question. Do you want to jump on and ask your question?
Sure. You had mentioned about the size of earthquakes, and so I was wondering what the difference was between what's considered a large earthquake versus a small earthquake.
Oh, that's a good question. I guess it depends. If you're a seismologist, you're the scientist that actually measures ground motion. They're probably so happy to get an earthquake that they'll consider any size earthquake, great. If you're an earthquake geologist and you run around the desert with a shovel, a big earthquake is any earthquake that leaves a surface trace, right? Evidence at the surface. So that's a big earthquake. So in general, earthquakes of magnitude, let's just say around 6 plus or minus, those are earthquakes that have surface displacement, and a magnitude 6 could have surface displacement on the order of inches, but a magnitude 7 or greater could be feet, tens of feet of displacement, whether it be horizontal or vertical. And if you were to ask an engineer, what is a large earthquake, they would say any earthquake that could damage a structure, right? So you can have a small earthquake that might have displacement of an inch, but if there's a building right on top of that fault or next to the fault, it could have damaging shaking, and you can have, you can distress a building. Whereas you could have a magnitude 7, which had, let's just say, displacement of 5 feet, but if your building's far away, the shaking's not as severe. So
Put things in perspective, Catherine comments, there are 51 earthquakes around the world already today. So,
wow.
Mimi, you have a great question that follows pretty naturally from what Steve just said. Do you want to ask that? Mimi Laughlin? I'm also happy to ask for you.
You have to unmute.
So Mimi asks, will there be a time when scientists could predict when a major earthquake could occur? And if so, do you see that happening in the near future?
Well, I know in the earthquake business, it's a lot of times they'll replace predict with forecast, kind of like in terms of weather, right? And it's in the context of probability. It's like weather. You can think of the forecast or prediction of earthquakes is analogous to weather forecasting, except that there's a lot more uncertainty with forecasting earthquakes, mainly because we don't have satellites that actually show like the magma or at depth movement, like weather patterns, like climatologists have. Although, like I mentioned earlier with GPS, that is like the best type of data that is being actively being collected that may help in aiding a forecast. So if there are some GPS sites that all of a sudden start moving much faster than they have in the period of record of measurement, then that would be a red flag. And then that would get the attention of the seismologists and the seismic hazard community. And then they would start looking at it. And that's when the seismology comes into. Now, if that same area starts kind of crackling, little teeny earthquakes start popping off at a rate that's greater than background, then between the GPS and the seismology, the probability of occurring has just increased. Now, right now, we can't say, oh, it will happen tomorrow or 5 days, but they put it within terms of like probability based on the record of past earthquakes and stuff. So, yeah.
I think that's real. That makes a lot of sense from the point of view of a science generalist, science curious person. That method makes a lot of sense to me. We have 2 more categories of questions, and I'm gonna ask Roy to ask the next one, and then for the folks who are asking about accessing the USGS data and Google Earth Pro, what I want to do is have Steve answer those after the raffle. So anybody who's interested in accessing Google Earth Pro and the USGS data, stay on after the raffle. The last question that we'll do with the whole group is from Roy. Roy, do you want to ask your question about volcanoes?
Yes.
Nice.
Is there a relationship between volcanoes and earthquakes? And is there a possibility that Las Vegas can experience a volcano?
There is a relation between earthquakes and volcanoes. In terms of when magma, I love saying magma, by the way. That's probably one reason why I'm a geologist, so I can say that. But yeah, when magma is extruded through the crust, it's pushing the crust, the land away to accommodate room for that injection. So that happens, you have earthquakes. So when a volcano is about to erupt, there's a whole series, essentially a swarm of earthquakes associated with that eruption. But the signal is completely different than a tectonic earthquake. Tectonic earthquakes, you can imagine, it's like shattering glass. When that glass shatters, you have vibration, right? When it breaks, that's the earthquake signal. But with a volcano, it's like a gopher burrowing its way up to the surface. It's just this constant movement. So you have like constant earthquakes. Now, with respect to Las Vegas being tectonically active place, it's not in the correct like seismotectonic environment. About 10 million years ago it was, because there's volcanic deposits everywhere, but not currently. Not to my knowledge.
We're just arriving a little late. Darn it. Awesome. So it's 4:27. AJ's going to hop on with the raffle. And then there are a bunch of questions that came in last about apps and data and even ground penetrating radar. So we're going to get to those briefly right after the raffle. Go ahead, AJ.
All right, for our raffle today, obviously you have to be here to win. So please say hi and show your video if you are. Jillian from Centennial High School. Are you here? Do we see her? Jillian.
I'm here.
All right. You won the first one. Congratulations. The next one is Latanya from Pine Middle School in Washoe County.
Hello, I'm here.
Yay. Congratulations. The next one is Michelle Gallivan from Sage Ridge. Hi, Michelle. I know you're here. I've seen you. Let's see, is she still here? Okay, the next one is Renee Miles from Reese Elementary in Clark. Are you here? Maybe not. Okay. And then the next one is Susan Ritter from Chaparral High School.
I'm here.
Yay! All right, congratulations. Let's see. Let's go back to, did we hear from Michelle Gallivan? Or Renee Miles? All right, so let's see, I have backup. And let's see. Looks like the next one.
Looks like those two both signed off. So go ahead and pick.
Okay. Okay. So then it would be Anton Love from Clark. Are you here, Anton? Oh, I have you as absent too. And how about Michael Mulligan?
I'm here.
All right. Michael's one. And the last one, let's see, Aaron Straight.
Hi, I'm here.
Right. Yay, all right, those are big winners for the day, congratulations. And also just a reminder that Megan will put the evaluation link in the chat box. I will also email it out later, but if you wanna go ahead and fill it out, it'll take you probably 1 or 2 minutes, which would be awesome. And then I know people wanted to follow up with Dr. Bacon with some more information. And the survey is in there. Thanks, Megan.
Yeah, thanks everyone who asked those awesome questions. Cool, so we're gonna start with a question about accessing USGS data. So Elaine asks, we're wondering how we get the USGS data set on Google Earth Images. Is that something that we can have access to?
Yeah, right. So luckily for us, anything that the USGS puts together, it's free to all of us. So I can provide a link to that source. You could also just Google USGS fault and fold database, and you'll see their webpage there. And they'll have a variety of different formats to that data. The one that you'd want is the KMZ data. That's the data that you can use in Google Earth. And it's really easy to download, and it's not a large file.
Cool. I just found, so I Google searched fault and folds, and I've got the earthquake faults web page up. And you said it's the cans?
The KMZ.
KMZ. Oh, KMZ.
And it might say, you can use it with Google Earth.
Yeah. Okay. So for those of you who are interested, I'm going to put that link right in the chat box. The CAMS or KMZ file is right near the top under the header that says download data. So another question on that same topic is, do you overlay the USGS fault lines on Google Earth Pro, or does it have to be, do the two have to be merged? Like,
No, you just open it up. So in Google Earth Pro, you just hit the file and then open, and then you select that KMZ file and it loads it up for you.
cool. Cool. That's awesome. Is Eric Murphy on the line? You had a similar.
Yeah, right here.
Hi. Do you want to go ahead and ask your question?
Yeah, thanks for the awesome talk, Dr. Baking. It was very, very interesting. In a past life, I worked as an engineer in the Bay Area. So obviously when designing structures or designing buildings, you have to take seismic design into a pretty serious consideration. What engineers do is they go onto USGS and they get these seismic design values. Some of them are like SDS values, or my memory is going, I think it's SD1 values as well, but it basically tells you what the site is likely to experience. And my question was if you knew about how geologists obtain those values.
Yeah, you can go to the USGS site, and there's, if I remember correctly, there's a link to probabilistic seismic hazard program, and they have all the maps and design codes that are used for engineering purposes. I think also there's the California Unified Building Code and Unified UBC.
It's the CBC, California
CBC,
Building.
okay, yeah, California Building, yeah. When I was using them, I was using the hard copy, but I'm pretty sure they probably have a more digital friendly version of it. But yeah, I mean, what I've done in the past is you put in a lat long, your building site, and then it returns like the probable, like the ground accelerations and some of the seismic design values, like what you were just talking about.
Awesome, thank you.
Cool. Latanya, are you on still to ask another technology related question? Go ahead.
Yeah, so my question was, how has ground penetrating radar impacted your field?
All right, that's a good question. It provides a great data set. Yeah, using geophysical techniques to characterize the subsurface is really powerful. It's a powerful tool. It could be cheaper than putting boreholes or drilling wells or boreholes to find information. Cheaper than digging a trench. It's not as it's more user friendly. You're not, like we always say, we joke around, if in doubt, dig it out. Meaning dig a hole and look at the dirt. But sometimes you might have a project, it might be real sensitive. It could be an archaeological site and you can't do any excavation. So ground penetration radar is a real powerful tool. There's uncertainties with it just because you don't have any real, verification of what's there, but there's been a lot of work done with it.
Awesome. Very good. So we'll wrap up on this last one. There were some comments that came in about apps that people can use to monitor the location of earthquakes for folks who are science curious. One of the suggestions is called QuakeFeed. Steve, are there any apps that you recommend for people who are interested in this topic that they can use?
In this, the topic is, again, sorry, you broke up on my end a little.
Oh, no problem. So there were a couple comments about people using mobile phone apps to monitor earthquake activity around the world, sort of for those of us who are interested in the information. What do you use? Do you have any that you'd recommend?
You know, I don't have any app personally on mine, but I have friends who do. And whenever there's an event of like greater than X magnitude, they'll get a text, and it'll tell them where it is. And,
cool.
and I believe you can make it specific to a geographical region, so you're not getting 50 texts in the last hour like we just were told.
Totally. Yeah, QuakeFeed, it sounds like, is a popular one. Just getting some messages.
Oh, okay, all right.
Awesome. Great. Well, thank you so much. Thanks everybody who stayed on after. And from Beta, I'll also share that out in the resources. Thank you so much. Right on. And Elisa says, thank you. Let's give Steve a little round of applause. You can use your reactions. Yeah, awesome.
Oh, can I say something?
Yeah, go ahead.
Not that I haven't said anything. Hey, I want to thank all of you, for teaching our kids. I think it's wonderful. And it's totally needed. And the fact that you all are right here, right now, shows a lot. And it makes me really happy. So thank you.
Ditto. Yay.
Ditto. Yes.
Thank you.
Lots of
Thanks,
warm fuzzies
Gary.
to end the call on. Thank you.